Hello, and welcome to this class in Electronics Communications. My name is Aaron Dahlin, and it is my pleasure to be your instructor. Let's get started. Today, I'd like to give a brief introduction to the class, a brief introduction to communication systems. The majority of our time will be focused on information theory, and just a heads up, we're going to be talking about the mathematics, specifically the logarithms that we'll be using throughout this class. The class itself is divided into 4 sections. The first is information theory. From there, we'll move to analog radio. That includes things like the traditional AM radio and FM radio that you might have in your car. Next comes digital radio. From there, we move to the closely related topic of computer networks. And we conclude by talking about subjects such as antennas, radar, and satellite communications. As we progress through the class, you'll find out that the tests are basically divided along these lines. So this is approximately exam number 1, exam number 2, exam number 3, and finally exam number 4. To get us started, let's look at a general model of a communication system. We start with a source of information, in this case, a person talking into a microphone. That microphone is connected to a transmitter. The transmitter is connected to an antenna, and the antenna broadcasts the signal. Some distance away, there is another antenna connected to a receiver. We'll let this receiver be connected to a loudspeaker. The last thing in this model is you listening to that receiver. Once again, this is the transmitter, and this is the receiver. This piece here between the antennas is known as the channel. And one thing that we can't forget, something that's going to dominate a lot of our conversation, is noise. All channels will suffer some degradation due to the noise. You may have experienced this as lightning strikes that you hear in your radio receiver. Now, our objective in this general model is to pass a message. We pass a message from the transmitter through the channel to the receiver. Before we move on, we should make a note, and that is regarding the channel. The channel can take on many different forms. It could be radio, as implied above. It could also be a cable. It could even be fiber optic. Oh, there is one more thing I should mention. As we progress through this class, we are going to be adding additional complexity to these transmitters and receivers. We're going to start out with simple things like amplitude modulation, and when we're done, we're going to be talking about how computers communicate back and forth between each other, or things like the Bluetooth headset that you might be using right now. As for the rest of our discussion today, we're going to focus in on this person. Specifically, we're going to talk about information. What types of messages are we trying to convey through this chain of transmitter, channel, receiver? In this particular case, we're showing a person speaking, such as I'm speaking to you right now. However, this could also be considered a computer. One computer talking to another computer over some type of channel. Again, that could be radio, cable, fiber. Please understand that this concept of information is going to be with us throughout the entire class. We are always going to be asking ourselves, how much information can be passed from the transmitter through the channel to the receiver on the other end? At this point, I'm going to ask you to pause the video. What I'd like you to do is go to the links below, and there you're going to find 3 videos about information theory that are hosted on Khan Academy. Please watch those and then come back and we'll do a quick overview and then move forward to see how that information about information links into the rest of this class. Now that you've watched those videos, let's do a quick mind map, specifically about the information source. I think you'll agree the information source generates, let's do that in a different color. So we can say the information source generates a message. We could say that that message contains information. We could also say that that message is encoded as data. Back to our information, I think you'll agree that information can be measured. I think you'll also agree that the information contains a component of surprise. In fact, the more surprised you are, the more information there is. Moving back to the other branch, you could say that data contains a stream of symbols. So contains. And those symbols can be processed, they can be stored, and they can be transmitted. In many ways, much like this video. My computer, for example, is a source of information. It generates a message. That message is encoded as data, as a series of ones and zeros. And those streams of symbols are processed, stored, and then transmitted to you. If we look at the simplest example for data, we can talk about a coin. We can say that a coin flip contains one bit or one unit of information. And we could let the heads, so if I were to flip this coin, you could ask a question. You could say, was that a heads or was that a tails? And that would be one question for every time the coin is flipped. Every time the coin is flipped, you have to ask a question. Now, that is, of course, assuming the coin is a fair coin. If it was a loaded coin, for example, if it had 2 heads, then there would be no information contained in the flip because no matter what the flip was, it would always come up as heads. So a fair coin, you have to ask one question or one bit of information is generated for every coin flip. Let's ask a question that's a little more complicated. We'll start with a deck of playing cards. So the first thing we do is get rid of the jokers and the instructions. And then we will have a person select a card at random. In this case, we'll choose the 2 of hearts. The card is put back in the deck and it's shuffled up a little bit. Now, here's what we need to do. We need to determine which card was picked. How many questions do we need to answer or ask to determine what the card was? Well, one way to do that is to say, was your card that? Was your card that? Is this your card? Is this your card? How about this? Or this? Or this? Oh, there it is. So in order to do that, we had to ask 1, 2, 3, 4, 5, 6, 7 questions before we finally got our 2 of hearts. That's not the most efficient way, because maybe that 2 of hearts was on the top, in which case 1 question was needed, or maybe it was on the very bottom, in which case 51 questions were needed. A much better way to ask that would be to lay the cards out like so and ask, is it in this pile or in this pile? And you can see it there, so we can say it's not in this pile of cards. So there's one question. Was it in the left or was it in the right? So you got rid of half the cards. Now you do it again. You spread out the cards and you say, is it in this pile or this pile? And they say it's not in this pile. So that's 2 questions that we had to ask. So 2 questions. And we just keep subdividing it again and again. So now, is it in this pile or this pile? Okay. So there's 3 questions. And once again, is the card in this pile or this pile? You say, nope. There's 4, 5 questions, and finally we can say, is this your card? If the answer is no, then your card was definitely this. So in this particular example, we asked 1, 2, 3, 4, 5. We asked 6 questions to determine what the card was. Moving back to the computer, it goes something like this. We start here at the top, and we ask a question. Was it in the left pile or the right pile? So 0 or 1. And we're going to call this the first level question. So level 1. Based on that, you then ask another question. Was it in the left or the right pile? So 0 and a 1, 0 and a 1. So that is your second level. And you see that the first level, there were 2 options. With the second level question, there are now 4. If we continue on, we'll see that there are now, how many possibilities on level 3? Looks like there are now 8. And if we were to continue on, you could see that it would be 16, then 32, 64, 128. This path where we went from here to here to here would be 0, 0, 0. This path would be 0, 0, 1, 0, 1, 0, 0, 1, 1. Now we can look at this path, and we call that 1, 0, 0, 1, 0, 1, 1, 1, 0, and finally 1, 1, 1. I believe those Khan Academy videos called this the message space. We can tabulate this real quick. I think you saw the pattern. You can ask n number of questions. So 2 raised to the nth power is described as the message space. And we saw that as n increases, the message space increases. So if n is 1, there are only 2. Is the card in the left side of the deck or is the card in the right side of the deck? If you ask 2 questions, there are 4. If you ask 3, there are 8, 4, 16, 5, 32, and 6 finally brings us to 64. Earlier, when we talked about a coin flip, we said that there was 1 piece of information for every flip. Is it a heads or is it a tail? So n in that case is 1, which means you can identify 2 unique things. For our cards, there were 52 cards, so that means we're somewhere in between the n is 5 and n is 6. Sometimes you can identify the card by asking 5 questions. Sometimes you can identify the card by asking 6 questions. If you wanted a more exact answer, you could say that 2 to the n is equal to 52. Solve for n. Now our rules for logarithms, which we'll cover in a moment, our rules for logarithm will tell you that if you want to get n by itself, you need to run that through a log base 2 machine, and you run the other side through the log base 2 machine. When you're done, you'll end up with n, because log base 2 undoes 2 to the n, so you end up with n is equal to log base 2 of 52. And then if you remember your change of base rules for logarithms, that works out log of 52 divided by log of 2, giving us a final answer of log 52 divided by log of 2, which is 5.7. On average, you would ask 5.7 questions to identify a particular card. About those logarithms, let's do a little sidebar here. As we get started, you should know that logarithms are going to be used quite often in this class. We're going to be using logarithms of base 2 and logarithms of base 10. This is a good time to pause the video and go find a note card because you're going to want to write these rules down. We'll start with the product rule. That tells us the logarithm of some base a for the product of x and y is equal to the logarithm base a of x plus the logarithm base a of y. That's a very useful property for logarithms because it tells us that a multiplication operation is replaced with an addition operation. The next rule is the ratio rule. That rule states that the logarithm of base a of x over y is equal to log of base a x minus log of base a y, which means that a division operation becomes a subtraction operation. The next rule is the power rule. For logarithm base a of x raised to the nth power, that is going to equal n log of that base a x. Okay. So that means this n essentially gets moved in front. So that's a useful property. And finally, the change of base rule, which I used in our example. Log of base a of b is equal to log of some base, we'll use base 10 in this case, of b over log of base 10 of a. Or, if you prefer, you could use the natural log of b over natural log of a. Doesn't matter which one you use. We did use the change of base rule right here, and you can see that's still keyed into the calculator as log to the base 10 of 52 divided by log to the base 10 of 2. We could also have keyed that in as natural log of 52 divided by natural log of 2, and I believe we get the same answer of 5.7. Before we end this logarithm conversation, I wanted to talk about this piece right here. You recall that n is an exponent, and in order to solve this particular problem, we had to break n out of jail. And we did that by taking 2 raised to the nth power and running it through the log base 2 machine. If we were in class, I would have brought in this book and I would have showed you this picture about the Sneetches. And I would have called this machine here, this machine that puts stars on the bellies of Sneetches, I would have called that f of x. Then I would have gone on to another part of the story where we have this machine. This machine takes stars off, and I would have described that machine as g of x. So let's put that together. We have this book by Dr. Seuss, and in that book we have a star on machine, technically identified as f of x is equal to x plus 1, because it puts a star on the Sneetch. We also have a star off machine, technically identified as g of x is equal to x minus 1. And what we're going to do is we're going to combine these two machines. So we're going to take this machine here, this x plus 1 machine, and we're going to couple it to a second machine where we have x minus 1. Again, this was f of x, and this machine here is g of x. Our Sneetch, upon entering the f of x machine, gets a star added, and upon entering the g of x machine, a star is taken off. mathematically we would say g of f of x is equal to x in this particular case. Now, we could put the machines in the other order. We could have x minus 1 here. We identified that as machine g of x, coupled to the x plus 1 machine, which we identified as f of x. And same thing happens. Our sneak enters, a star is taken off, and then a star is added back. And we would say that f of g of x is equal to x. These are known as inverse functions. Some other examples. On your calculator, there's a 1 over x button. So if you enter a number, for example, 5, and then you hit the 1 over x button, and then you hit the 1 over x button again, you end up with the number that you started with. So if this is x, we end up with x. Here's another one you might be familiar with, and that is sine theta. The inverse machine is arc sine theta, or sine inverse of theta. We can do that on the calculator as well. So if we have sine of, say, 60 degrees, there it is, root 3 over 2, and we can do inverse sine of answer, and we should end up right back where we started with. There's 60 degrees. One more you might be familiar with is the natural logarithm of x has an inverse machine of e raised to the x. If we let x equal, say, 5, okay, so 1.6, and now if we let e raised to answer, there it is, we return back with 5. And that finally brings us to the point I wanted to make, and that is log to the base 2 of x has an inverse machine of 2 raised to the x. If we wanted to get fussy, we would say that 2 log base 2 of x is equal to x, or if we reverse the order of the machines, we would say log base 2 of 2 to the x is equal to x. In both cases, whatever went into this chain of machines is the same thing that comes out because they are inverse functions. Now we can go back to our original example right here. So remember what we said. We said log base 2 of 2 to the x is equal to x. So that's where we solve this. We ran both sides of the equation. We ran this side of the equation, and we ran that side of the equation through the log base 2 machine. We ran both sides through the star off machine. Let's regroup here. We've shown two examples. One was how much information is contained if we flip a fair coin. In the next example, we asked how much information was contained in identifying a single card out of a complete deck of cards. And we determined that to be about 5.7 questions. Let's work another example to make sure we understand the operations here. Let's assume we have 5 symbols. We'll use color to represent the symbols. There's brown. We'll use symbol B, orange. There's an O, yellow, green, and blue. And we use the Spanish word there. Okay, so 5 symbols where the symbol is represented by a color, and each of those symbols is generated at random. And the question we need to answer is how much information is generated per symbol. We say 2 to the n is equal to 5. Using our log rules, back to the Sneetches there, we need to run it through the star off machine. So log base 2 of 2 to the n. So what we do to one side of the equation, we do to the other. So log base 2 of 5. So this here gives us n, and then we use the change of base rule. So log base 2 of 5 is log of 5 over log of 2. Going to the calculator, that's log of 5 divided by log of 2. So n in this case is 2.32 bits, or questions if you prefer, per symbol. If it helps, you could think of it this way. I'm thinking of a color. Can you guess which color I'm thinking about? And you would have to ask, on average, 2.3 questions to determine which color I'm thinking of. Yet another way of saying that is each of these random symbols has an information of 2.32 bits. Right? 2.32 questions needs to be asked to determine the color. Just to make things a little bit more interesting, I might ask a question such as, how much information is contained in 20 symbols? It's as if we're playing the game 20 different times. I'm thinking of a color. I'm thinking of a color. I'm thinking of a color. So each time we play that game, we end up generating 2.32 bits of information. Using dimensional analysis, we would say that there are 20 symbols, and we know there are 2.32 bits per symbol. And dimensional analysis, of course, would have you cross off units. So we're left with 20 times 2.32, which is 46.4 bits of information. So if we were to play the game 20 times, you would have to ask 46.4 questions on average to determine what the color sequence was. As we end, let's do a quick review of this video. We started out talking about the general model of communications, where we said all communication systems contain a transmitter, a channel, and a receiver, and that channel is always plagued by noise. Next, I asked you to look at those videos from Khan Academy, where you learned about an information source, how it generates a message. That message contains information, and that information can be measured. How is it measured? Well, one way is to talk about this decision tree, answering a series of yes/no questions to determine how much information is there. We tabulated it here. So if you ask this or n many questions, you can have this many possible things to identify. For example, a coin generates 1 bit of information for every toss, and here was a deck of cards where if you pull out a card, it would take 5.7 questions on average to identify what that card was. And we also did another example dealing with 5 randomly generated symbols, and we determined that you would need approximately 2.32 questions per symbol, where a symbol in this case is the color. When you come back next time, we're going to talk about encoding, and then we'll move on to some of the first lessons in analog communications.